You look at a straw in a glass of water, and you say, "Ah, it looks bent." You watch a sunset, and you know the sun is already below the horizon, but its light is curving through the atmosphere to reach you. You read about black holes, and they tell you light can't escape their grasp. And you think to yourself, "Ah, yes, light bends." Well, here's the thing. You're wrong. Not just a little wrong, but fundamentally, philosophically, completely wrong. Light doesn't bend. I know, you're looking at the straw. You're picturing Einstein's famous prediction about starlight curving around the sun. You're thinking of a prism splitting light into a rainbow. All the evidence seems to be screaming at you that light bends. And I'm telling you it's the greatest trick the universe has ever pulled. You see, the word bend is a lie. It's a lazy metaphor, a clumsy analogy we've been using for centuries because we didn't know any better. We look at light changing direction and our brains, wired by evolution in a world of rocks and balls and rivers, immediately think, something must be pushing it. Something must be pulling it. We think of light as a little particle, a photon bullet, being nudged off course by gravity or by water. It seems so intuitive, so obvious. But nature doesn't care about what seems obvious to a bunch of apes who just learned to walk upright. So let me ask you the simple question at the heart of this grand illusion. Why does light bend? Is it because gravity pulls on it? Is it because glass or water slows it down and makes it swerve, like a car with one wheel in the mud? That's what you've been taught to picture. That's the cartoon in your mind. But what if I told you that light is the most stubborn, straight-laced thing in the entire cosmos? What if I told you it is, in fact, going perfectly straight, and that the bending is not in the light, but in the very stage upon which it performs? The truth is far stranger, far more beautiful, and will lead us down a rabbit hole to a realization that challenges not just how we see light, but how we see reality itself. Because to understand why light bends, you must first understand what straight even means. And that is a question that will collapse everything you think you know. So, let's look at this misconception we all carry around. It's a perfectly reasonable one. It comes from living in this world. You throw a ball, it goes in a parabola. Why? Because gravity is pulling it down, curving its path. You shoot a bullet, it eventually arcs toward the ground. Same reason. A force is acting on it, changing its velocity, which means changing its direction. Now, we learn that light is a thing. It comes from somewhere and goes somewhere. We see it change direction. So our brains, brilliant pattern matching machines that they are, shout, "Aha!" Same thing. A force must be acting on the light. Take the straw in water. The story we often hear goes like this: light travels slower in water than in air. So when the light beam hits the water at an angle, one part of the wavefront hits first and slows down, while the other part is still in the air going fast. This difference in speed makes the whole beam pivot, like a tank with one track moving slower than the other. It bends. It's a wonderful mechanical picture. It feels right. It uses gears and levers in your mind. And for the straw, it's not wrong, but it's only scratching the surface of a much deeper truth. It's like describing a beautiful symphony by saying, "Well, you see, the violinist moves his arm back and forth." You're not lying, but you're missing the music. Then, we have the big one, gravity. Einstein comes along and says the sun's gravity bends starlight. And what's the popular picture? The sun's gravity grabs the light and pulls it in, like a planet's gravity pulls on a passing comet, making it curve. We have this ingrained idea that gravity is a force that acts on things that have mass. And then they tell us light has no mass, but is still affected by gravity. A contradiction. So they invent ideas like photons have relativistic mass or other hand-wavy fixes to keep our force picture alive. We are desperately trying to shove this square peg of light into the round hole of things being pushed and pulled. This is the problem we've built for ourselves. We have two different phenomena: light going through water and light passing the sun, and we explain them with two different, complicated mechanical stories. One about slowing down, another about a mysterious force acting on a massless thing. It's clunky. It's inelegant. Nature is not clunky. Nature is not inelegant. So I ask you, what if these two things, the bent straw and the bent starlight, are not two different puzzles? What if they are, in fact, the same phenomenon seen through two different windows? What if there is one single, beautiful, utterly simple principle behind both? A principle so fundamental that light must obey it, not because it's being forced, but because it is the very essence of how light moves through the world? That's the itch we have to scratch. That's the tension. We have our common sense picture, and we have a sneaking suspicion that it's all just a shadow on the wall of a deeper cave. let's put aside light for a moment. Let's talk about something much more familiar. You're a lifeguard. Imagine you're sitting in your tall chair on the smooth, hard sand. Suddenly, you see someone drowning out in the water. Your job is to get to them as fast as possible. Now, you can run very fast on the sand. But in the water, you can only wade or swim much slower. So what path do you take? The perfectly straight line from you to the swimmer? That would be the shortest distance. But is it the shortest time? Think about it. If you run in a straight line, you spend a lot of that line slogging through the slow water. You're taking the geometrically shortest path, but it's a slow, stupid path. You want to maximize your advantage, your speed on the sand. So what do? You run farther on the sand. You take a path that's not straight. You angle your run down the beach so that the distance you cover in the fast zone is longer and the distance you have to struggle in the slow water is shorter. You run a longer distance overall to get there in a shorter time. Now, draw that path. It's a straight line on the sand, then a sharp kink at the water's edge, then a straight line in the water. Two straight segments, meeting at an angle. Not a curve. A bent line. But here's the fascinating question, is that the optimal path? With a sharp kink? What if, instead of a sudden change, you could sort of curve your run? Start angling slightly on the sand, so you enter the water already pointed more toward the swimmer? Would that save you even more time? Try it in your mind. You realize there's one perfect path, a specific angle at the shoreline that gets you there in the absolute minimum possible time. Not the shortest distance. The shortest time. And that path consists of two straight lines meeting at a very specific angle. Now, let's bring light back into the picture. Think of the air as the fast sand. Think of the water as the slow, waiting zone. A light ray comes from the air, hits the water's surface, and goes to a point underwater. It wants to get from point A to point B. Does it take the straight line, shortest distance path? No. It does exactly what you, the clever lifeguard, do. It takes the path of least time. It spends more of its journey in the faster medium, air, and less in the slower one, water. It hits the water's surface at a specific angle, and then suddenly changes direction. That's refraction. That's the bent straw. The bending is not because the water is dragging on it. It's because light is an efficiency expert. It's a cosmic courier that always takes the fastest possible route between 2 points, given the landscape it has to travel through. But wait. Let's test this idea. What about a mirror? Light hits a mirror and bounces off. Angle in equals angle out. Where's the fastest path there? The air is the same everywhere. Imagine the lifeguard again, but now the swimmer is back on the sand, reflected across the shoreline. The fastest path to the real swimmer is blocked by the water. But if you imagine a mirror swimmer on the other side of the shoreline, the fastest path to that imaginary point is a straight line, which hits the shoreline exactly where you need to bounce. So the law of reflection, angle in equals angle out, is also the path of least time. It's the same principle. So we have one principle, the principle of least time, explaining both reflection and refraction. One beautiful, unifying idea. No talk of slowing down causing a pivot. Just a simple, almost lazy rule, I will take the quickest way. But if light is always taking the fastest path, why does it look bent? Because time and speed are the rulers it uses, not a tape measure. It's optimizing in a different currency. And when the exchange rate between media changes, when the speed of light changes, the shortest path in time is no longer the shortest path in space. The bending is an illusion of our spatial thinking. Light isn't swerving, it's being ruthlessly efficient. It's going straight in the currency of time. But now we have a new, much deeper question. This works for water and glass. But what about gravity? There's no clear shoreline in space. The speed of light in a vacuum is constant, isn't it? So how can there be a fast and slow zone for light near the sun? What landscape is it optimizing its travel time through now? So we've discovered light's secret rule, take the path of least time. It's called Fermat's principle. And it explains the straw, the prism, the mirror. Beautiful. But this rule poses a terrifying, wonderful question to the universe. What does least time even mean when gravity is involved? You see, with the lifeguard, the map was simple. Sand here, water there. Speeds are constant in each region. The landscape of speed is flat, with a sharp boundary. But gravity isn't like that. Near a planet or a star, gravity doesn't create zones with different constants. It creates a slope, a gradient. Imagine now you're the lifeguard, but the sand itself gets softer and harder to run on the farther you go from your chair. And the water gets deeper and harder to wade through the farther you go from shore. Everything is changing, smoothly, continuously. What's the fastest path now? It's not two straight lines with a kink. It would be a curve. A smooth, continuous curve, because you are constantly making micro adjustments, trading off distance in one area for a slightly better speed in another. Light does the same thing. But here is the crack in reality. For light in a vacuum, there is a commandment. A sacred rule from Einstein's special relativity: the speed of light in a vacuum, c, is constant. It is the universe's speed limit. It cannot change. So if the speed of light is constant, how can there be a path of least time? If the speed is always the same, then the shortest time path is just the shortest distance path, a straight line. Gravity should have no effect. Starlight should not bend. Unless the thing we are measuring distance and time with is itself affected by gravity. Think of it this way. You have a map of a mountainous region. The map is flat paper with straight lines of latitude and longitude. You draw the shortest path between two towns, a straight line on the paper. But if you actually walk that straight line on the paper, you'll be going straight up and down enormous mountains. It will take you a very long time. The true shortest time path on the actual ground is a trail that winds around the mountain, following the valleys. On the flat paper map, that sensible trail looks curved. But on the real, wrinkled terrain, it's the straightest, most efficient path you can take. The flat map is wrong. It's a distorted picture of the real, uneven territory. That is Einstein's revelation. Gravity is not a force that pulls on light. Gravity is the curvature of the map itself. More precisely, it is the curvature of spacetime, the fused fabric of space and time. The presence of mass like the sun warps spacetime around it. It creates valleys and dimples in this four-dimensional fabric. And light, that utterly obedient cosmic traveler, still follows its one rule: take the path of extreme time. Technically, it follows what's called a geodesic, the straightest possible line in a curved geometry. But straight in a curved space doesn't look like our flat space straight. Draw the straightest line on the surface of a globe. It's a great circle, a curve that goes around the bulge. To us looking from the outside in 3D, it looks curved. To a bug living on the 2D surface of the globe, it feels straight. Light is that bug, living in the four-dimensional fabric of spacetime. It goes perfectly straight along its geodesic. But we, with our stubborn, classical 3D brains, slice that 4D path into a sequence of snapshots of path through just space, and we see a curve. We see bending. The bending is not in the light's action. The bending is in the stage. The stage itself is warped, and light is simply being a good actor, following the boards. So the starlight grazing the sun, it is not being pulled. It is simply following the straightest line available in a universe where the sun has made a deep, dimpled valley in spacetime. It is the cosmic equivalent of the lifeguard's curved path on the gradually changing sand. The speed of light is still constant locally, at every point along its path. But the geometry of space and the flow of time are different at different points, and light's unwavering commitment to its least time geodesic forces it in our 3D view to appear to arc. We have one principle: extremal travel time. It explains the straw and the starlight. The straw is about light optimizing through a sharp change in the properties of space, the speed of light in a material. The starlight is about light optimizing through a smooth change in the geometry of spacetime itself. The bending in both cases is the same phenomenon viewed through different lenses, light taking the fastest route through the landscape it finds itself in. Only the nature of the landscape has changed from a simple property map to the very shape of reality. Now, I can see you might be thinking, that's a lovely metaphor, Feynman. A curved stage, a straight actor. Very poetic. But what's the machinery? How does mass tell spacetime to curve? And how does light know how to find this geodesic path? These are the right questions. Let's peek under the hood. Don't worry, we won't get lost in the tensors. We'll look at the beautiful ideas. First, how does mass curve spacetime? Think of a trampoline. A very heavy ball in the center creates a deep depression. That's the standard picture, and it's useful, but it's incomplete because it's only showing the curvature of space. The trampoline surface is 2D space. We're missing time. The full truth is wilder. The sun's mass doesn't just make a spatial valley. It also makes a time gradient. Clocks run slower in a gravitational field. A clock near the sun ticks slower than a clock far out in space. This is tested, proven. GPS satellites have to correct for it. So the dimple the sun makes is a dimple in spacetime. It warps the there and it warps the when. This combined warping is what guides everything: planets, apples, light. Now, how does light find its geodesic? It doesn't know anything. It doesn't calculate. It simply obeys the local laws at every point. There's a beautiful way to see this, using our principle of least time, but now for a curved stage. Imagine you're back to being a lifeguard, but now you're on a hillside with a curved slope. The slope affects your speed. You run faster downhill, slower uphill. To find the fastest path, you'd have to solve a calculus problem. You'd consider every possible twisting path from start to finish, calculate the total time for each, and pick the smallest one. That's the variational approach. Light, in a sense, does this, but not by thinking. Nature does it by having the laws of motion be such that the actual path taken is always the extremal one. In the flat space case with refraction, this leads to Snell's law, n sin equals into sin 2. That's just a mathematical answer to the lifeguard problem. It's Fermat's principle boiled down to an equation for a sharp boundary. In the smooth, curved spacetime case, this leads to the geodesic equation. This equation is the answer to what is the straightest possible path on a curved manifold. It looks complicated, but its soul is simple. At every instant, move in a way that feels like going straight locally. For light, which always moves at speed c, this has a stunning consequence. In flat spacetime, a straight line in space is also a straight line in a spacetime diagram, a diagonal line at 45 degrees if we scale time right. In curved spacetime, the geodesic will deviate from that flat space straight line. When we project that 4D spacetime path down onto our 3D space, that deviation looks like an acceleration, a curve. Let me show you a way to almost derive the bending of starlight using just the equivalence principle and the idea that light falls. Einstein's happiest thought: a person in a closed elevator cannot tell the difference between being at rest on Earth, feeling gravity, and being in deep space accelerating upward at 9.8 meters per square second. Gravity and acceleration are locally equivalent. So, imagine a beam of light shining horizontally across an elevator that is accelerating upward. To someone outside, in inertia, the light goes in a straight line, but the elevator floor is accelerating upward to meet it. To someone inside the elevator, the light beam appears to curve downward, tracing a parabola. Why? Because the floor and the observer are rushing up toward the light's path. Now, by the equivalence principle, what looks like acceleration in deep space is gravity on Earth. Therefore, a horizontal beam of light in a gravitational field should also curve downward. But and this is crucial, this Newtonian prediction, using the equivalence principle alone, gives you half the correct bending angle. Half. Einstein first published this result in 1911. But by 1915, with his full theory of general relativity, he had the complete picture. The bending is due to the curvature of space and the curvature of time. The Newtonian-style falling argument only accounts for the effect of time slowing down near the mass, the time part of the spacetime curvature. But space itself is also curved. It's stretched radially near the mass. This spatial curvature contributes an equal amount to the bending. So the full general relativistic effect is twice the naive prediction. This was the clincher. Eddington's 1919 expedition measured starlight bending during a solar eclipse. The measured angle matched Einstein's full prediction, not Newton's half prediction. Light wasn't just falling in a Newtonian sense, it was tracing the straight line in a geometry where both rulers and clocks were distorted. So, let's connect our two benders. For the straw and water, spacetime is flat. No gravity. The landscape is a property of the material, the index of refraction, n, which is just the ratio of c to the speed of light in that material. Fermat's principle, least time, in this flat space with varying n gives us the bent path. For starlight near the sun, the landscape is spacetime geometry itself. The mass of the sun sets the metric, the mathematical function that tells us the distance between nearby points in spacetime. This metric is curved. Fermat's principle, reinterpreted in curved spacetime as follow a null geodesic, gives us the bent path. One majestic principle, two different manifestations. The universe is telling us that the paths of light are not about forces, but about optimization within a given geometry. The geometry can be a property geometry of materials, or the fundamental geometry of the universe. Light is the ultimate surveyor. It doesn't move through space, it reveals the shape of spacetime. Once you see it, once you understand that light doesn't bend, but rather exposes the lay of the land, your whole view of the universe shifts. It's like putting on a new pair of glasses. Suddenly, light becomes not just something you see with, but something you see through. Think of it. Every time you see a lens focus light in your eyeglasses, and a camera, and a telescope, you are not watching light being forced to curve. You are witnessing a human-engineered distortion of the optical landscape. We sculpt glass into shapes that create a specific geometry of slowness, so that light's relentless quest for the fastest path will bring all rays to a single point. We are not bending light, we are designing hills and valleys for it to run over, knowing perfectly well how it will optimize its route. We are landscape architects for photons. And every time an astronomer sees a so-called gravitational lens, a distant galaxy whose image is stretched into a perfect arc, or multiple images around a closer galaxy cluster, they are not seeing light being magically pulled. They are staring directly at a topographic map of a spacetime valley. That elegant arc is a contour line of sheer mass. It is a cosmic fingerprint pressed into the fabric of reality. Light is the ink that traces it. This changes the very purpose of light. It is no longer a mere messenger bringing us pictures of things over there. It is a probe. It is the universe's own tool for surveying itself. By carefully watching where light goes and how long it takes to get there, we can weigh galaxies, detect invisible dark matter, and test the very foundations of geometry. But let's go further, let's go personal. You are sitting there, held to your chair. You think gravity is pulling you down, but now you know about the curved stage. So what's really happening? You are, right now, attempting to fly through spacetime in a straight line, a geodesic. But the Earth's mass has created a curvature. Your geodesic, your straight line, would naturally carry you through the spacetime curved by the Earth, and that path, when projected onto our 3D space, happens to intersect the planet's surface. The ground is accelerating upward along its curved world line to meet you. The force you feel on your seat is not gravity pulling you. It is the electromagnetic force of the chair pushing you, preventing you from following your natural, geodesic freefall. You are, every second, being pushed away from a straight line in spacetime. The bent path of your life, sitting still on Earth, is the forced one. The straight path is the terrifying, exhilarating one of orbit or freefall. And here is the profound, philosophical pivot. This means space and time are not the fixed, passive stage upon which the drama of physics plays out. They are actors in the drama. Dynamic, flexible, responsive. Matter tells spacetime how to curve, spacetime tells matter, and light, how to move. The bending of light is the universe's way of revealing this conversation. It is the clearest signal we have that our deepest intuitions about the void, that it is nothing, that it is empty, that it is just there, are childish illusions. The void has a shape. The void has a structure. The void participates. When you see a sunset, you are not just seeing light bending through air. You are witnessing, in the most common spectacle, a gentle echo of the same principle that governs the orbit of planets and the fate of galaxies. The principle that straight is not what you think it is, and that the true fabric of reality is a flexible, four-dimensional tapestry, forever being woven by the mass and energy within it. Light is our shuttle on that loom, and its thread always runs true. So we arrive at the mind-bending core of it all. The collapse. Let's state it plainly. There is no such thing as a universal straight line. Think about that. Throw away your ruler. Your ruler is a lie, a convenient local fiction. In a flat room, on your desk, it works fine. But launch it into the cosmos, and it becomes meaningless. Straight is not an absolute concept. It is a local concept, defined entirely by the geometry you find yourself in. Light does not follow our idea of straight. It defines straight. It is the gold standard. When we see light bend, it is the most glaring proof that we are the ones thinking crookedly. We are the ones clinging to a flat map intuition in a spherical universe reality. This means that all of physics, the entire story of motion, from an apple falling to Earth orbiting the sun to a galaxy spinning, is not a story of things being forced to curve. It is the story of things being left alone to go straight. Let that sink in. The planets are not being pulled by the sun. They are coasting. They are simply following the straightest possible paths, the geodesics in the curved spacetime created by the sun's mass. They are doing exactly what a stone does when you drop it, and exactly what light does when it passes by. The only difference is their speed through time. The law is one law. Geodesic motion. Force, in its Newtonian sense of a mysterious pull acting at a distance, evaporates. It was a magnificent, useful illusion. What we call the force of gravity is just the feeling of our 3D minds trying to interpret 4D geodesic motion as an acceleration. We feel pushed because we are being prevented from following the true, straight, freefall path. And here is the final, beautiful, terrifying symmetry. Remember the straw in water? We explained it with Fermat's principle of least time in a landscape of varying light speed. But in general relativity, we can also think of that glass of water as curving spacetime in a very specific, limited way. The effective slowing of light in a medium can be represented as a tiny, artificial curvature of the spatial dimensions. The two pictures, property landscape and geometric landscape, begin to whisper to each other. They are different languages describing the same profound truth: motion is geometry. Whether it's the geometry of an index of refraction or the geometry of mass-warped spacetime, the path taken is the extremal path in that geometry. The universe, at its heart, is a geometric engine. So when you see light bend, you are not seeing an exception to the rules. You are seeing the purest expression of the rules. You are seeing the universe's blueprint. You are seeing that space is not empty, time is not uniform, and straight lines are the most interesting curves in the world. So, why does light bend? We started with that simple question, a child's question, and we found it led us not to a simple answer, but to a revolution. Light doesn't bend. It reveals. It is the universe's most honest surveyor, tracing the true, wrinkled shape of reality with unwavering fidelity. The bend is in us and our flatland expectations, and our stubborn insistence that space is a static stage and gravity a ghostly force. There is a joy, in seeing through the illusion. It's not a joy of knowing more facts. It's the joy of seeing more clearly, of having the confusing, disjointed pieces of the world, a straw in a glass, a sunset, a warped galaxy in a telescope, suddenly snapped together into a single, breathtaking picture. One principle, from the shimmer of a pond to the edge of a black hole. The principle of the straightest path, the fastest time. The principle that what is shaped by what is there, and that everything moves to tell that story. When you understand this, you don't just understand light. You understand that you are living inside a dynamic, responsive, geometric entity called spacetime. And you understand that the greatest wonders of physics are not hidden in distant galaxies or massive machines. They are right here, in a glass of water, in the fading light of day, waiting for anyone with the courage to ask a simple question and the patience to follow the light wherever it leads, even, and especially, when it leads away from everything you thought you knew. That's the adventure. That's the fun of it. Keep looking.